In this video, we're going to talk about the actual AC equivalent circuit that we're going to be using to do our AC analysis. And so remember, the basic idea is if we have these linear amplifiers, so if we have small signal inputs, then we can use superposition, which means we can do our AC and DC analysis separately. So when we're doing our our AC analysis, what we want to do is we want to deactivate our DC sources. So deactivate any DC sources that we have. And so in this case, we have two DC sources. We have our VDD and we have our VGSQ. And because both of those are voltage sources, we can deactivate a voltage source. So DC voltage source is going to be deactivated by making it 0 volts. And how do we make it 0 volts? Well, we're just going to short it. So by shorting that, these 2 points, so basically right here, of course, we're just shorting across that, and here we have some implied voltage source, so it's not explicitly drawn out, but something like this to ground, so of course we're just shorting that. And so we can redraw this circuit, and so it's going to look very similar, of course, so we have something like this, and so from our source, we're still going to ground, and now from this side as well, we're going through RD to ground on our drain side. And this voltage across RD is still going to be our V out. And so sorry, now this is our small signal, so that's a lowercase v, lowercase o. And off of our gate side, we no longer have that VGSQ, but rather we just have that small signal, lowercase v, lowercase I. So that's connected between there and ground. And of course we have some drain current in here, so that's going to be our small signal drain current I sub D, and some small signal gate voltage V sub GS, and so like we saw in the last video, our V sub GS is just equal to the VI in this case. Okay, so that's sort of the first step in terms of creating our AC equivalent circuit, but just like with our BJTs, we can take this a step further, and we can say, how can we make this transistor something that's a little easier to handle? And so we're going to do that with a small signal equivalent circuit. So small signal equivalent. So really up until this point, we would have been fine with larger signals because any harmonics from the MOSFET would still be represented in this circuit. But now when we transition to the small signal equivalent, we're assuming we have that condition that we talked about in the previous video. So in our small signal equivalent circuit, again, we're replacing that transistor. So how do we characterize that transistor? Well, let's list a few of the things we know about our ideal transistor. So for a MOSFET, ideally we have 0 current into our gate terminal. So 0 current into gate. In practice, we know we'll have some really small amount of leakage current, but let's ignore that for the moment and say ideally we just have 0. As we saw in the previous video, we found out that our small signal drain current, or our AC drain current, is just equal to our transconductance times our VGS. And as we looked at previously, when we were looking in the previous unit at MOSFETs, we found there's also some small signal output resistance, R0, which is equal to the slope of our ID versus VDS curve. So this is the partial derivative of ID with respect to VDS. And so actually 1 over the slope of that, and that's evaluated at the Q point. So for VGS equals VGSQ. And so that's a little bit complicated, but if you want to see more analysis on that, you could go back to page 5-17 in the notes, and we'll look at a specific equation for this R0 value. But ultimately what it goes back to is we said that in our saturation region, if we have our family of IV curves, we said in our saturation here, these aren't actually perfectly horizontal lines, but rather they have some non-zero slope. And so I've drawn that kind of exaggerated. But the slope of that curve here in saturation is going to be 1 over R0. So that's what that value is. So putting all of these things together, we can then create a model for our transistor. So let's start by defining our 3 terminals. So let's say we have in blue, just for clarity, we have our gate over here, we have our drain over here, and then down here we have our source. So we say we have 0 current into our gate, which means it's just going to be an open circuit. So if we don't have any current, that's not going to be connected to our drain. It's also not going to be connected to our source. So there's no current flowing in there. Now, between our drain and the source, though, we are going to have current. And so we can represent that with a dependent current source. So we know for an N-channel FET, which we have in this particular circuit we're considering here. So really right now let's clarify that we're looking at an NMOS device. So in this case we have current flowing from the drain to the source, and we know that the value of that, as we said in this second bullet, is going to be GM times VGS. So this is going to be GM, and I'm going to switch to use our phasor notation, so capital V, capital GS. And so that's flowing from our drain to our source. And of course that VGS value is just the potential between our gate and our source. So VGS as defined over here. And this small signal output resistance we can see as a change in our drain current as our VDS is changing. So of course our VDS is between here and here. And so in order to have that voltage affect our drain current, we need to put this R0 resistor between our drain and the source. And so this would be our lowercase r0, our output resistance. And then the current coming into this point is going to be our drain current, I sub D. And so what we can see then is that if our VDS, which again is going to be the voltage across this resistor, is changing, we're going to have some change in our drain current, which is exactly what this lowercase r0 is sort of characterizing. Okay, so that is our small signal transistor model. So now what we would want to do is just sort of connect that to our circuit up here. And so we could see that our source, of course, is at ground, and our VI is connected between our gate and ground. So coming back down here, all we would have to do is add in our VI over here. So again, switching to phasor notation, capital V, lowercase I, that's connected between our gate and source, where our source is grounded. And then at our drain, we also have that resistor RD, which is connected between our drain and source over here. And our V out is defined at our drain. So I can just add our resistor RD, and then our output V out is going to be defined right here. And we can also note that that is the voltage between our drain and our source. So again, that's going to be phasor notation, uppercase V, lowercase ds. So again, just for clarity, all of this here, so not including that ground, is our actual transistor model. And then everything exterior to that highlighted circle is going to be the rest of our circuit. So that's going to change depending on the topology of our circuit. So this is our transistor model. So a couple other important things to note. So first of all, let's define these small signal parameters, our GM and our R0. So we've actually seen them before, the GM just in the previous video. So we said that is 2 square root of Kn times IDQ. And so again, what we can see from that is we have to do that DC analysis to get our IDQ before we're able to even deal with this small signal equivalent circuit. The other equation we had for our small signal output resistance we considered earlier. So we said that was 1 divided by lambda over IDQ, where that lambda was our channel length modulation parameter. And we said this is also equal to VA over IDQ. So depending on what information you're given, you can use either one of those two forms of that R0 equation. And again, we see that this R0 is dependent on our Q point location. So again, our DC analysis has to come first, and then once we have our Q point values, we can do our AC analysis. So another important thing to keep in mind is that we're making a bit of an assumption when we leave this open circuit between our gate and our source, because ultimately remember that we have that MOS capacitor, which is between really our gate and our substrate, but typically the substrate and the source are tied together. So what we're assuming is we're assuming that our frequency is low enough so that that capacitor is acting like an open circuit. So we're assuming our frequency, and we're talking about frequency of our input signal here, and therefore all of the other voltage and current signals in the circuit. So we're assuming frequency is sufficiently low so that our gate capacitance is negligible, or in other words, acting like an open circuit. So negligible. And keep in mind the impedance for a capacitor is equal to 1 over j omega c, or negative j over omega c. And as we saw in some of our lab activities, if we have transients, if we have switching going on, that can lead to issues because of course that looks like basically for a DC, this is going to have, a capacitor is going to appear like an open circuit, but as we have really quick changes, that appears like a high frequency, so we can have relatively large amounts of current flowing in no time unless we have appropriate circuitry sort of leading into our gate. So one other thing to touch on really briefly is, of course, this is for an NMOS device or an N-channel device as we set up there. Of course, we have an analogous thing for a PMOS device or a P-channel device. And so typically in this class, at least, we're going to be looking at NMOS devices, but of course there are PMOS devices, and PMOS devices are especially important as we combine them with our NMOS, and then of course we create our complementary MOS or CMOS devices. So here we can see the small signal equivalent circuit for a PMOS device. Just like with our BJTs, for the MOSFETs, it's the same basic model for our NMOS. We've just switched our current directions and our voltage polarities. So now we're interested in our source to gate voltage and our source to drain voltage. We also notice that our drain current is flowing out of the drain, and this current internal to the transistor is flowing from the source to the drain. Other than that, pretty much everything is identical here.